Hello everyone. In this lesson, we will continue to study the frequency domain analysis model of continuous system. Today, we will discuss the spectrum of aperiodic signals. The main contents include, first, the derivation of spectral density function, that is, Fourier transform. Second, the physical meaning of Fourier transform, and the last one, conditions for the existence of Fourier transform. Let's start with the derivation of the spectral density function. In the first knowledge module, we have learned the definition of periodic signal and aperiodic signal. For periodic signal ft, when its period t approaches infinity, it becomes an aperiodic signal. When discussing the spectrum of periodic signal in the previous section, the spectral coefficient of periodic signal is expressed by Formula 1. When t approaches infinity, obviously its spectral coefficient is close to zero. For periodic signal, its spectrum has three characteristics: discreteness, convergence, and uniqueness. For discrete spectrum, its spectral interval is 2 pi over t. When t approaches infinity, its spectral interval is also close to zero. So, this discrete spectrum becomes a continuous spectrum, and its amplitude is infinitesimal. It is not appropriate to use Fn omega to represent the spectrum, although the amplitude of each spectrum is infinitesimal. The relative size is still different, so we should introduce the concept of spectral density function. Let's look at the first formula. When t approaches infinity, Fn omega approaches 0. Then t is multiplied by Fn omega. According to the relationship between period and the frequency, it can also be written into the form of Fn omega over f. Obviously, it's an bounded function. It can be called the spectrum value on unit frequency band. If we let Fj omega equals t times its spectral coefficient, when t approaches the limit of infinity, Fj omega can be described by Formula 2, and Formula 2 can be simplified to Formula 3. Here, Fj omega is called spectral density function or spectrum function. In fact, you have already learned Formula 3. The mathematical representation of spectrum density function is Fourier transform that you have learned before. It is expressed by Formula 4. That is to say, the process of finding Fj omega from Ft is called Fourier transform. In general, Fj omega is a complex function, so it can also be expressed by Formula 5. Here, the absolute value of Fj omega is called the amplitude spectrum. Phi omega is called phase spectrum. It can also be expressed by Formula 6. Here, Fj omega is represented by its real part and imaginary part. Well, what is the inverse transform of Fj omega? Actually, according to the Fourier transform we learned before, the inverse transform of Fj omega is the time domain signal Ft. It is expressed by Formula 7. Therefore, there is a Fourier transform pair Formula 7 and Formula 8. Formula 7 represents the forward Fourier transform. Formula 8 represents the inverse Fourier transform. It can be abbreviated as Ft double-headed arrow Fj omega. Well, what is the condition for the existence of Fj omega? We will discuss it later. Let's look at physical significance of Fourier transform. Another representation of Ft can be derived in this way. This is the definitional formula of ft. Ft is a real function. Fj omega is a complex function. It can be expressed by its modulus and phase. Replace Fj omega in the original expression. We can get another formula Ft, and then according to Euler formula, e to the power of j phi omega and e to the power of j omega t can be expressed in the form of cosine function and a sine function. Then we can get the following formula. Here, the absolute value of fj omega is even function, and the cosine function is also an even function, so after its modulus is multiplied by cosine function, the result is still an even function, and the sine function is an odd function, so for the second integral, its integral value is 0. And the integral value of the first term can be calculated according to the half-period integral. Then we can get another description of Ft, Formula 9. It can explain the physical meaning of the Fourier transform. We can transform Formula 9 into other form. That is to multiply 1 over pi with its integral formula. By analyzing such a formula, we can find that integral represents sum. This is a cosine signal. This is its amplitude. Therefore, the physical meaning of Fourier transform can be explained in this way. Its physical meaning can be expressed as Ft. It is the sum of infinite continuous cosine signals with infinitesimal amplitude. Its frequency range is 0 to infinity. There is another form. Ft is represented by formula 11. Well, what is its physical meaning? Ft can be expressed as the sum of infinite continuous exponential signal with infinitesimal amplitude. It occupies the whole frequency domain. That is to say, the range of omega is from negative infinity to positive infinity. Finally, let's look at the condition for the existence of Fourier transform. Here is its sufficient condition. The sufficient condition for the existence of Fourier transform is that Ft is absolutely integrable in an infinite interval. All energy signals meet this condition. That is to say, the Fourier transform of energy signal exists. But when we introduce the concept of delta omega function, there are more types of function allowed to do Fourier transform. This will be discussed in the following content. Let's make a summary. First, we introduced the concept of spectral density function, that is, Fourier transform. This is the expression of the forward Fourier transform. Then, we studied the physical meaning of Fourier transform. Ft can be expressed as the sum of infinite cosine functions with infinitesimal amplitude. Last, the condition of Fourier transform is that Ft is absolutely integrable. Of course, it is a sufficient condition. You should note the expression of the inverse transform of Ft. In the next section, we will learn the spectrum characteristics of typical signals. This class is over. Thanks for your listening. Goodbye.